Hey everyone, welcome to another special episode of Eigenbros.
Yes, indeed. Welcome, ladies and gentlemen, once again. So we have a very special guest today. You probably recognize her from her YouTube channel, Looking Glass Universe. She also is a PhD candidate at Cambridge University. Mithuna Yoganathan. I think I said the last name correctly. Yes?
Close.
Almost got it.
Excellent.
Yeah.
Pretty close.
Yeah, nailed it.
Yeah.
I had a little delay there.
Yeah, you had to think about it. You had to remember that little mental image.
Yeah. So thank you for coming on the show.
Yes.
Yeah, appreciate it.
Oh, no worries. Yeah, no problem. Thanks for having me on.
Yeah, so hopefully our listeners will get a good sort of idea. Most of them are physics students. There's a lot of undergrads that listen to our show. Enthusiasts too.
Yeah.
There's a lot of undergrads that listen to the show. And if you haven't seen her channel already, go check it out. It's really good.
Yes, indeed. It's got some really, really nice content on there.
Yeah.
Very good explanations of things.
So one thing that I kind of wanted to ask you about, because it's everyone's journey is so different.
Yeah.
And especially people that are on YouTube, they typically have an even more like how would you say,
What?
kind of non-traditional way of getting to physics. So can you tell us a little bit about your journey, like just your life path, so to say, to physics or something?
When I was in high school, I would, like, when I was younger, I would never have pictured myself in physics because I was one of those people who really loved like English literature and I really loved like learning languages, and I never paid any attention to science class or maths class. I was in like the bottom set for maths class, which, means that like at 13 they decided I was an idiot and so like I wouldn't be able to do maths. And so like, that was never on my radar. And then we did this class when I was 16 where we learned about cosmology, and I was just like, this stuff is amazing. And so then I read Bill Bryson's A Short History of Nearly Everything. I don't know if you guys have read that.
Never heard of it.
Okay, it's fantastic. Anyway, so I read it and I finished it and I was like, yeah, I'm going to be a physicist. And so I suddenly just like changed course completely, like took all the maths classes, worked really fucking hard. I don't know if I can swear on this podcast.
Oh, yeah. We've said much worse.
Yeah.
Okay, good. Very good. So like I did that and then ended up in like a physics class in university, and like was enjoying it, but then I just like accidentally stumbled into maths as well while I was there, which like was really weird because all this time I'd like thought that I was bad at maths. Like I could pass if I had to, but like I didn't think that this was something for me. Then I started taking like abstract algebra. I don't know if like either of you had this experience.
Yes, this is ringing true very much so. But yeah, continue on.
All right. And so, I took abstract algebra and I was like, what on earth? Like, this is so amazing. Like, I can't believe they didn't tell me about this in school. Completely loved it. Changed majors to pure maths, which is so ironic. Like, I would love to go back and tell some of my maths teachers from when I was like, really young that that's what happened. And so I majored in that. But then how I got back into physics is I started this YouTube channel, and then I had like a 6-month break where I was like, okay, I'm just going to make YouTube videos, but like no one wants to see YouTube videos about maths, so I'll just make it about like quantum physics. I mean, I've taken some classes in quantum physics, that shouldn't be hard. So I started making videos about quantum physics and realized I didn't know anything about quantum physics after all.
Like every good physicist.
Yeah, exactly, right. Yeah. So I was like, oh yeah, like I can solve the Schrodinger equation. That's what quantum physics is, right? And it's like, oh, I'll make some videos where I don't use any like hard maths. And then I realized that like, if I couldn't use maths, then I didn't even know like the first thing about quantum mechanics.
Yeah, quantum's one of those things where it's pretty much like when you try to start using language and linguistics to explain it with no math, you're pretty much in a sinking ship. It's like,
exactly.
It's a race to the bottom with that.
Yeah, exactly.
You pretty much always need the math with quantum.
Yeah.
But anyway, I'm sorry I interrupted you. You were saying?
No, not at all. No, I think that's interesting that you say that, because because I had a maths background, the way I'd approached quantum mechanics up until then had been very mathematical. Like I'd been, looking at it from a sort of functional analysis point of view, and I was like, oh, I get this because it somehow goes deep into it. But I think that there's something to be said about like trying to understand just the very core principles of it with just language. And it was when I tried to do that and failed many times that I realized that not only did I not understand quantum mechanics, but there's like lots of interesting mysteries still left there. And so that's why I ended up going back into physics and doing my PhD in like sort of a quantum foundations related field.
Yeah, so Mithuna, you started with math, yes, in college.
Yeah.
So then you are technically an applied mathematician.
Yeah.
Very interesting. I've always tried to figure out like what's the difference between an applied mathematician and a physicist. It's literally like, to me, I don't see the difference.
Yeah, right. I think so. I think that like there's generally no difference, but in my particular field, so I'm in quantum computing / foundations. The difference is that like I'm very rarely doing anything useful, like looking at an equation and then like trying to find approximate solutions. Instead, I'm like writing proofs. And so so the techniques are much more like from maths.
I should have known. The proofs are always the separator with mathematicians and physicists.
Oh yeah, yeah. They have to prove. They have to make the tools, Terence.
Yeah, exactly.
To use,
build that foundation.
Yeah. It's respectable. In fact, we need more people like that because if I had the time to go back and actually study the math really well enough, I would love to do foundations of quantum mechanics stuff. Experimentally, that stuff is still. I would love to do that at some point.
Yeah.
But speaking of, what's your favorite interpretation of quantum
mechanics? Okay. I feel like everyone thinks that my favorite interpretation is Bohmian mechanics because, like, ages ago, I made some videos about it.
Right. Yeah.
If Bohmian mechanics, if you haven't heard of it, is a hidden variable interpretation of quantum mechanics, which like gets derided by physicists so much. And I think that I made these videos just because I was like annoyed that all these physicists would say all these stupid things like, oh, like hidden variable interpretations of quantum mechanics are not possible. And like these people are just trying to deny like what quantum mechanics is telling you.
Yeah.
But that's just a misinterpretation of Bell's theorem. And Bohmian mechanics exists and is an interpretation of quantum mechanics. So that proves that like hidden variables are possible.
Yeah.
And so I made these videos just like explaining this. And also explaining why you might want a hidden variable interpretation of quantum mechanics. Because basically, like, it means that you don't have to accept things like superposition. You can still think that particles are in one place and have one momentum and follow a deterministic rule for, like, where they end up. Which is, I think, really nice. But it's not my favorite interpretation. I don't know about you guys, but
you heard it here, folks. Hear your first, folks. So she's not.
Yeah, that's right.
She's not tied to Bohmian mechanics.
Yeah. So that's. I mean, it's not my favorite, but I mean, you're totally right about physicists kind of trivializing the interpretation, which is kind of silly. But I think the best. One professor put it to the best answer that I ever heard from one professor was, "It's not renormalizable," and I was like, "Okay, all right, that's valid." I was like, "That's probably the most valid argument I've heard." Okay, all right, it's not renormalizable.
Yeah, exactly.
That's fine.
I think that is the knockdown argument for Bohmian mechanics. You just can't make it work with like relativity. And it like
certain things aren't
really
invariant.
ugly when you try.
Yeah, certain things aren't like invariant. But anyway, in case you wanted to know a little bit of it for you listeners out there.
So Mithuna, I really liked your video on spin and angular momentum. Me and Juan actually had this debate like literally 2 days ago. And I was like, oh, let me go check out Mithuna's channel to, check and see what she's got going on there. And literally it was like the exact question that we were debating. We were saying,
oh, really? So what were you guys like talking about? What like conclusion had you guys drawn?
I just was confused. I was like, how do we know that there's angular momentum with a particle? Like, I get because there's angular momentum for the listeners too, to recap. There's angular momentum and spin with an electron, let's say. But there's a classical experiment called the Stern-Gerlach experiment where there's a deflection of a particle, and it's using magnetic field. So you would naturally assume, that makes sense because there's a magnetic moment in electrons, so it gets deflected by a magnetic field. Why the hell does that have to include angular momentum? But then your video beautifully summed up, that you actually need that angular momentum, or else you'll always get a flipping, or you'll always get one direction in which the Stern-Gerlach pushes the particle. And I was like, that makes so much sense. Of course, it involves this angular momentum, gyroscopic effect that we always see with the classic, the rotating tire. I don't know if you've seen that. And it's one of these things that's classically just defies your intuition, but then when you start putting it in that framework, it really is clear to see. So I say, I was like, hats off to you for that video.
Thank you. I'm really glad, because I had the exact same confusion. Like, especially my earlier videos, they're basically me staying one step ahead of like what I'm teaching. So it'll be me being like really confused, just like you guys, like, why on earth why do we make this about angular momentum? Like, angular momentum is not related to this. And like just getting really frustrated and like spending 2 weeks just thinking about it. And then eventually it clicks and it's like, oh yeah, just make a video. And then I guess when you see the video, you're like, oh, she makes it seem like that was so obvious, but it wasn't obvious.
Yeah. No, it's not obvious. We had to write a bunch of equations on the whiteboard and stare at them and then argue with each other.
And then eventually just said, screw it.
Think about this. We'll think about this some other time.
But you solved it. That was, it's usually, I think people take that for granted a lot. When they hear a simple explanation and it clicks so quickly, they don't realize how much work that you've put into that explanation. It's just like when you see equations, they're so simple and whatnot, and people will think of this. We also had this argument where we were saying how Juan was arguing in the favor of low-hanging fruit has been taken from physics. And then I was arguing that it wasn't low-hanging fruit at the time. Those things take a lot of work to get to. It's just that when we see it in hindsight, we see these nice, beautiful, elegant equations as they are. But all of those equations had blood and sweat and tears poured into them at levels that we can't even comprehend, probably.
Yeah, absolutely. Like, I think in some ways, like, those equations are more impressive than what we do now, because we have the tools already. Like, we already have, the axioms of quantum mechanics laid down. But imagine trying to wade through all these analogies and things when you really have like no clue what's going on. Like, I was thinking about yesterday, like de Broglie's equation. I was trying to figure out like why it was true, and realized that there's no way he could have even known that it was vaguely true. Like, he made some funny analogy which has loads of holes in it, but like that's how you have to do it, and that's very uncomfortable.
Is this the one that you did the video on?
Well, I don't think I've made a video on this. So it's just like the wave equation, the way that momentum and the wavelength are related to each other.
You know what? I actually was literally thinking about this like a couple days ago as well.
Really?
Yeah. And there's a really good video by Khan Academy.
Oh, really?
That shows the mental process that he went through. So it all started with light, actually.
Yes.
So light, you can already get the wave equation with light. It's just the what is it? HC over lambda equals HC over lambda. You can get that from the Einstein total equation. The total energy equation, the classic rest mass plus relativistic energy, or rest energy plus relativistic energy equation. You can get that with the photon. So you can get basically what looks like the de Broglie wave equation from that. So really what de Broglie saw was that from the double slit experiment, you were getting this weird interference pattern with the light, right? And we said, okay, we thought light was a wave at first, but then the Einstein, what was it called? The Einstein photoelectric effect showed us a particle.
Yep.
So then de Broglie was like, screw it, like maybe everything is a wave and a particle. So then he said, I'm going to use basically the same kind of
the particle wave duality
equation with this. And then eventually it was experimentally confirmed that, this actually was true when they did it with electrons too.
Yeah, right. But this is like a huge leap, right? Because there's no reason to believe that if it's just true for like light, and there could have been many other interpretations that could have fit with that data as well.
Yeah,
you're right. I think there was more to it.
His PhD committee must have been so upset. In fact,
I know, right?
This was because this was his defense. This was his PhD thesis. I remember reading.
Really?
Yeah, I remember reading it too.
You've read it. What's it like?
Yeah, it was. Well, it was kind of. It's kind of silly to read now if you go back to really? Like have a good laugh. But it's like
I thought it was supposed to be really elegant.
Well, I mean, in hindsight, I guess it's kind of at the time it must have been. But still, like I can imagine being a professor at the time thinking this guy's insane.
Totally. And he wants a PhD off this.
But I think it wasn't. He was a wealthy guy, wasn't he?
Not sure.
I think so.
I think.
Du Bois sounds fancy, so I'm assuming
it does, doesn't it?
I remember him. I remember one. I don't know. Somebody was very, very, very well regarded in terms of money, and so maybe
a lot of these guys were back in the day.
Oh, science was a rich man's game. I'll tell you that.
Yeah, absolutely.
So, yeah, we would have not have been in that vicinity at all.
Well, I think we would have probably been lifting cinder blocks or something. But anyway,
it's funny because. There's another interpretation. Funny enough, I actually loved. I love looking up at quantum foundation stuff. So there's a formulation called the de Broglie Bohm, I think, or some. Who is it? No, Schrödinger. I forget who it was, but they were basically trying to combine wave equations. I think it was Schrödinger. He was trying to combine wave equations to sort of be, how would you say? Not necessarily like sort of have this particle wave duality or something. You guys can Google it. Yeah. Look it up. It's actually really cool since we were on the topic of de Broglie and foundations of quantum mechanics. Yeah, but I don't know if you've heard of this interpretation.
No, I haven't. So I know that Schrödinger was thinking along these lines when he got to his equations, but this is something separate from that?
Yeah. I'm trying to remember if it was Schrödinger. Maybe it was somebody else. I'll have to go back and insert audio here. No, I'm just kidding.
Yeah. Right.
Just
send me the paper later.
Plug in the actual interpretation so you guys can Google it. But it
sounds good.
Really cool stuff. Go check that out.
Yeah.
So whatever the hell Juan's talking about, somebody put in the
comments. Yeah, exactly.
But
maybe you're going to have to put a little note being like, he's just blowing smoke.
Exactly.
It'd be like just a bunch of question marks, huh?
No, so actually, one thing that actually puzzles. Well, me and Terence get into a lot of arguments about quantum mechanics.
Oh yeah,
that's awesome.
In fact,
that's great.
One of them being, we want to hear your input on this. Superposition. So superposition is a topic that. Personally, I'm comfortable with it.
No, you're not.
But Terence is...
Shut up.
Terence is not.
Yeah, exactly.
Terence is very upset.
Don't listen to him, Mithuna. He's delusional.
Yeah.
So he isn't. So what is your take on superposition?
Right.
Yeah.
Okay, my take is that it's very mysterious and maybe like the mystery of quantum mechanics. Because... so I'm not sure what parts... you guys are happy with or which ones you're debating. But fundamentally, when we're looking for an interpretation of quantum mechanics, I feel like what we're really looking for is an interpretation of superposition and of measurement. So what was your take on it?
I think that's probably pretty good to sum it up.
Yeah, that's exactly it.
I guess the thing that we always have trouble with is wondering how you can tell something is in superposition. But actually, I had a really interesting interview with a guy named Dietrich Leifried, and he works at NIST. It was during the APS March meeting thing, and he actually explained how they measured the superposition of particles without disturbing the state.
What do they do?
I wish I could sum it up for you. So unfortunately, I'm going to have to leave you with a big question mark. Because I still haven't gone back over the audio and actually really understood
it.
But hopefully at some point we can release that audio.
That would be great.
Yeah.
Sorry. I'm just going to restart my camera.
Oh, yeah.
You're good. But the measurement process, I just want to butt in and add to this. The measurement process is a nonlinear one. So because you have, and that's kind of the main problem, right?
That's right.
Yeah, can you expand on that for some of our listeners?
Yeah, sure. Okay, so when people first came up with quantum mechanics, they were sort of happy to say quantum mechanics is this thing that only happens to small things. Everything else is still classical. So this is like the interpretation that like Bohr favored, for example. And like if you think about this is already very strange, because it's like saying, you know, there's these like two different universes. They have different like rules of physics that apply to them. But they were sort of happy with this. But then let's say you're not, and let's say you want to say that everything is quantum mechanical, which makes sense. Like there should be one theory that applies to the whole universe. So then you might be like, okay, well, we're just going to say everything is quantum mechanical. Like how far can we get? The problem is that quantum mechanics obeys this like Schrödinger equation, which like has this property that it's linear. But that means that like sort of the states like evolve smoothly. Like the problem is that when you want to get from that to what we see in our sort of classical world, you have this like measurement postulate which says that this state that was evolving smoothly suddenly has to like collapse into one place. So as an example, like imagine you had an electron that you started off confined to a small spot. The Schrödinger equation would say that it would like spread out smoothly. But as soon as you try and measure it, like if you try and like, you know, put some device to look where it is, then the measurement postulate says that it has to like instantaneously pick up all of its mass from all over the universe and just like squish it back into one spot, which means that like you can't get that behavior from quantum mechanics itself. Like Schrödinger equation can never reproduce that kind of madness, and so that means that like
irreversible.
Yeah, exactly. Right. It's crazy. And so you can't assume that you just have the Schrödinger equation. Like measurement is something that needs to be explained separately or done away with. So like my favorite interpretation is actually the many worlds interpretation, because it just goes, what if there are no measurements? Like what if we just stop believing in measurements and then it all works out? It's really nice.
So shout out to Sean Carroll. Mithuna is also many worldser.
Right.
+1 on that one.
Yeah. Very interesting. Quantum mechanics is one of these topics you can just spend all day on, I feel like. So because of that, I'm going to force us to switch gears here a little bit. So Mithuna, awesome. I guess I wanted to also learn some more about your personal life. So so you're originally from Australia, yes?
That's right. Yeah.
Okay, and do you have any like siblings?
Oh, I do. Yes, I have one brother.
Okay, and is he also into like science, physics, that kind of stuff?
No, so he's younger than me, and so my parents, I'm obviously brown, so my parents obviously wanted me to become a medical doctor.
The classic.
I was a great... I know. So I was a great disappointment to them.
Do you have an Indian background?
No, so my parents are from Sri Lanka originally.
Sri Lanka, okay. Shout out Sri Lanka.
Yeah.
And so when I told them that I wanted to be a physicist, they were like, "Oh, well, I guess we only have one child now."
Yeah, but you're a different kind of you're a doctor, but just not a medical one.
Right, exactly. So eventually my brother, who's 1 year younger than me, did get into medicine, and they were very proud of him, and he became a doctor 6 years later, and they were like, "Oh, we're so happy to have a doctor in the family." And I was like, "Hey, I'm also a doctor." And they're like, "Yeah, but like a real doctor."
Brutal.
Yeah, I'm thinking about bigger things. Thank you, Mom and Dad.
Exactly.
None of this petty earthly.
They're thinking about bigger checks.
Yeah. Okay.
Yeah.
Okay, I guess
exactly.
so. I'm not stuck on human affairs. I'm thinking globally.
There you go.
Yeah. Oh, yeah. Totally. Tell that to my parents.
But when you get rich and famous from your YouTube channel, then they'll be singing another tune.
Yes, exactly.
Oh, yeah, absolutely.
Yeah. When society collapses and they need a physicist to figure out how generators work, then they'll come running to us.
Mm-hmm.
Yeah.
Your time is coming. Don't you worry.
Yeah, we're all waiting. Exactly. We're all waiting for that.
Right. Except, I'm a theoretical physicist. I definitely don't know how to make a generator.
That is true.
In principle, you know.
In principle.
In principle, you know, and that's good enough a lot of the time.
Yeah.
That's right.
It just might take you a long time, but that's okay. You'll get it eventually.
There's a bunch of engineers out there. They'll figure it out.
There you go.
Yeah. You just say, this is how it works, okay? And then they put it together. But
but continuing on, Mithuna, so I guess you
I do want to add, because you did, this is sort of related to kind of some of the personal life stuff. So because you said your trajectory was kind of strange. It was sort of stochastic. It was sort of random. It was kind of weird and
fancy words.
Right.
To end up at physics. But I understand that the system I guess not in America, is a lot more like because most of our listeners are American. The path there is sort of predetermined, if I remember correctly.
Right. So it depends where you are.
Yeah.
In the UK, that's certainly the case. Actually, it's kind of scary in the UK. At 16, you basically decide which subjects you're going to specialize in. You only get to do 3 from that point on, and then you can pick a major before you start university. And so if you pick maths as your major, you only do maths for your whole 3 years, which I think is really messed up.
He was being sarcastic.
No, I was being serious.
Right.
Oh, really? Okay.
I would never,
I think it's great if you know that that's what you want to do beforehand. But I think the problem is that it's very hard to know beforehand. So, I completely changed career paths, or career trajectory at 16. So I would have been too late if I had been in that system. But I was kind of lucky in that in Australia it's not like that. And in particular, I'd done this IB certificate. And so it meant that I had to, they forced us to do subjects in a huge range of subjects. And so then I got to try out everything. And then I went into a Bachelor of Science, which I guess is sort of similar to the American system in that you can do any subject that counts as science. And in fact, you can do a couple of subjects or a few subjects that don't count as science. So I did Japanese for a year, and I did a bunch of computer science courses. And it was really good to just see a range.
That's an interesting system. I've never heard of that.
Yeah, it is interesting.
Right.
Yeah.
Oh, no, what's it like in America?
No, in America it's very it's very linear. You take 2 years of random stuff that the university thinks that you should know because you're now a global. You're now a person of universal knowledge, so they want you to gather all that. Anyway.
Yeah. Well, I think that's great.
But yeah.
So what kind of subjects will they make you do?
So they would make you learn about U.S. history, U.S. politics, that kind of stuff.
English.
English.
I was so goddamn sick of English. I'm no offense, Mithuna, I know you love English and you got your passion in there, but god damn it, I don't want to read Anne of Green Gables anymore.
I love literature, so it was an easy A for me. But we have to take writing. We have to be, there's a certain quality assurance to the university system.
Oh, I love that. That's beautiful. I think that more universities should be like that. And as you said, I was doing my PhD in the UK, and so that meant that I was supervising undergraduates, and I felt really sad for them that all they were doing was maths, and all they knew was maths. It's really useful to have a bit of a broader base.
Sure, but at the same time, the trade-offs are very dire.
Yeah, there's a side. There's two sides of the coin because as American physicists, we're usually really fucking behind.
We're on the lower
end.
We're on the lower
science.
end of the rung. Yeah. It's very saying because
the international people come in and they are killing the game, and then we're all trying to just figure out what the hell x to the -1 power means.
Shut up. He's kidding, but nevertheless,
I wish I was.
This is we basically in the 4-year system, you have 2 more years of compiling all of physics, and a lot of the time it's not up to par with most international programs because. The equivalent is in America. The equivalent of their bachelor's is a master's here. So it's a little bit offset. So there's some trade-offs. Yeah, we're more worldly people. We're more, but at the same time, if you're doing this as a profession, it's kind of there's a lot of trade-offs.
Yeah. If the whole world was like that, we'd be in a good spot. But
yeah, it would be even playing.
So I've met a lot of mathematicians who went through the UK system, and this is going to sound extremely rude, but I've not always been terribly impressed.
You have or not been?
I've not always been so impressed. Like, yes, they're very, very technically good, but you need to be much more than just technically good to actually become a mathematician or a physicist, right? Like, you need to have a lot of creativity, which I worry is being stamped out by this other system.
I think in the American system, it's similar, though. I think anytime your institutions get too large, they just turn into kind of garbage in some ways.
This is something that's it's a sort of
bluntly.
But it's a philosophy, and I think me and Terence and a bunch of our classmates have had a discussion about the sort of movement or the philosophy that's adopted in most physics departments, which are the von Neumann approach, which is shut up and calculate.
Yeah.
Right.
Yeah.
Right.
Just don't even think about it. Just shut up, do it.
Yeah.
You know, it's
absolutely
good. Just know how to use a Schrodinger's equation. Superposition doesn't matter.
Exactly.
Just do it.
Right.
You know what I mean? So how do you think that maybe, because right now we're reaching almost a standstill in theoretical physics and a lot of physicists are just actually now they're starting to question the foundations of a lot of our knowledge.
Right.
And do you think it's a result of this philosophy where it's like maybe, we're not being creative enough or universities aren't incorporating more creative thought into that?
Oh, that's a great question. I think it's a little hard for me to say because I didn't go via the sort of high energy route, which is the, studying I did these courses, but I didn't really go into research in like quantum field theory or like gravity or anything like that. But my impression is that these fields are very stagnant, and part of the problem is exactly what you said, that to get into them, you have to have like really nailed the calculations. Like, you have to be super good at doing all of those very tricky calculations, but that means that you've spent a lot of time investing all of your energy into doing that. And I think that that's counterproductive to thinking about like what it means, or how could I change this, or like what's wrong with this. And I think that it would be a lot better for physicists to have a lot less of a like rigid like training and be less technically good, but be like able to think for themselves a little bit more.
I definitely like that philosophy. Another problem I've had with, or at least one perception I've had of the route that all physicists take in the U.S. is, we've experimentalists and theorists get lumped up into the same category.
Right.
So it's like if you're an experimentalist, you're learning so much theory. A bunch of times, by the time the experimentalist actually becomes an experimentalist, they're like just a glorified theorist who, they can't do anything in the lab. It's like it doesn't make sense really. You don't learn any experimental skills. So it's like we need a more nuanced approach towards I think physics training in the future, I guess you could say.
Yeah,
do you agree with that?
Yeah, so I think that in like what I've seen of from like the physics departments that I've been in, like people learn by far the most when they're doing their research. And so like I knew a bunch of people who had studied physics with me, who then went on to become experimental people, and like at that point they'd done all the same courses, they only had done theory. And so they were like thrown into a lab and it's like, here, fix things. Right?
Right. They're like, what the hell? I can't use equipment.
Yeah, exactly. What is this? But it was good for them. Like, I think that that's probably the way to learn. And maybe there needs to be more projects sort of incorporated into the undergrad. Maybe that could help, or like, the grad program. But I don't know.
Yeah, because applied physics or applied math, there are definitely, applied mathematics, I think it seems a lot more, how would you say, linear. I mean, at least the classes, the applied math classes that I've surveyed, are super interesting. By the way, they use a lot of. That's the first time I've ever seen fractional derivatives. It was like fractional derivatives. I was like, damn, what the hell is a fractional derivative? Yeah. So
Dylan Berger had some cool ass animations with that.
Yeah,
a few months ago, maybe.
Yeah. So that kind of blew my mind.
Put the link in.
Yeah, Dylan Berger. Go check him out.
Are you familiar with him, Mithuna?
No.
Yeah.
Well, you're on Twitter, so definitely follow Dylan Berger. He does all these really cool animations. We're going to have him on the podcast coming out this week.
Yeah, he's
Actually,
You've probably seen.
Now that you say it on Twitter, I think I have seen these
Inertial
animations.
Observer.
That's his name.
Does that sound familiar?
Yes.
There you go.
Yeah, he's
there
a cool
you go.
guy.
I know him.
He's an NSF fellow. At UC.
She is as well.
Oh,
Aren't you?
Am I? I don't think so.
Maybe
No.
not.
like no.
I thought for some reason I saw on your Twitter page that you were an NSF. My bad.
No.
He's projecting. He's like, yeah.
I'm like, she definitely should get the.
He's like, I would give her an NSF fellowship.
Oh, thank you.
Yeah, what was I going to ask? But I got caught up in laughing.
Oops.
So I kind of.
Oh, you were saying about your applied maths courses?
Oh yeah. But I was trying to connect the two somewhere. But anyway, it doesn't really matter. So
I ruined your train. Sorry.
Yeah, I was laughing. I was having too much joy.
Yeah.
Which isn't allowed in physics, by the way. So
No, exactly. No.
we got to be very stoic.
I think you were saying. What? Sorry.
I said we have to be very stoic. I'm sorry.
Okay.
Super
All right,
serious.
good. Well, I think what we were talking about was that applied maths is more linear.
Yes.
I don't know what he means by that.
It seems to be, because we're now differentiating, like we're advocates for differentiating or making more nuanced sort of differentiation between theoretical physics or maybe sort of applied mathematics in some sense, because there might be some overlap, I guess, with some physicists as well.
Yeah.
And experimental physicists. So I definitely on that. I agree with that 100%. And I still lost my point. So
Yeah. That's,
all right, I'm going to take this train.
No, it's because I'm coming off a bender from just finishing a manuscript draft. So
God.
So
Well, congratulations.
thank you.
How is your research progress right
Sorry,
now? Actually, Mithuna, that's a good segue, I think.
Oh God, yeah. I think my supervisor would like to know too.
I just let him know today, and he was very upset. He said, "I haven't seen." He said, "What?" He was just like, "I don't even know what." Yeah, so don't worry, you're not alone on that.
What was your supervisor's name again?
So his name is Richard Joseph.
Yes. Okay. Yes.
Great guy. But so what's happened is I've basically just finished my PhD. I finished writing the thesis January 30th, and I was supposed to submit, and it was all supposed to be fine. But as a maths physics person, I obviously am incapable of doing paperwork. And so apparently you were supposed to send them a form that says 2 months before you submit your thesis that you want to submit your thesis. Who knew? And so
bureaucratic stuff.
I know, my God. I know. And so I sent them that eventually saying I want to submit my thesis already. And then they spent a month and they emailed me back saying, yeah, you didn't fill out this form correctly.
Goodness.
Why don't you just take the damn paper?
I know. It's like I finished the thesis. It was such an anticlimax. Like I was working super, super hard. And then I finished it. And I was like, okay, I just want to send this somewhere. And then I realized I had to do all this stuff. And it's been like drawn out now over quite some time. And then in the middle of all this, I was so I'm in Australia right now, like on holiday essentially. I was gonna go back for my defense, but now we have no idea when that's going to be because there's no way I can get to the UK anymore.
Because there's a global pandemic going on, people.
Problems
That's
upon
right.
problems.
If you haven't heard,
That's right.
you know.
Yeah, exactly. Just in
How are
case.
you holding up during the COVID crisis?
So it's been stressful as it must be over there as well. I mean, it must be much
more stressful over there. I don't know.
I'm not sure.
Well, Americans are more, a lot of people say we're more free, but we're also dumber. So it's kind of a lot of people are making silly choices. But nonetheless, we're not gonna divulge on that. But
no, exactly.
No. So speaking of your PhD thesis, so what is give us a quick synopsis of what I guess you've studied, if you don't mind me asking. I guess.
I never mind anyone asking about my thesis. It doesn't happen very often. So basically, I'm interested in quantum mechanics and like what makes it so special from classical mechanics. Like you could just say, oh, well, like it's obviously that there's superpositions, or it's obviously that it obeys the Schrödinger equation. But these are all just like properties of the actual maths of quantum mechanics, and it's not like I could just write Newton's laws, for example, with different maths, and then be like, yes, this is obviously different from the other one because it has a different equation, but it's actually equivalent, right? And so you want to find, like, you don't want to point at like particular parts of the maths. You want to point at something that is like tangible, like something, like some property of quantum mechanics that makes it so like fundamentally different that like adding that to a classical theory is what gets you to quantum mechanics. So that's something I've been interested in. And so there's this, I don't know if you guys know a bunch about quantum computers. But what's interesting about them? Yeah, go on.
No, yeah, we discuss it all the time. We're experimentalists.
But of course, that's your field.
Yeah.
So we're not going to be comparable, but we know probably more than a typical physicist that's not in condensed matter.
Yeah.
Right. Yeah. Okay. Awesome. So like the thing that's special about quantum computers is that they aren't equivalent to regular computer. In that, for regular computers, like no matter which way you decide to build them, they're going to come out not being very different. Like the algorithms that you can run on both of them are the same. Whereas that's not the case with quantum computers. Like there are algorithms that you can only specifically write for quantum computers, and they'll only run on the quantum computer. And some of those are faster than what you could have written on a classical computer. And so like there's something fundamentally different about them. And so I wanted to understand, like, is that fundamental difference like the thing that's fundamentally different between quantum mechanics and classical mechanics? It seems like yes. And so if you can figure out in the quantum computer case, like what's so special about quantum computers, then you can figure out in like the general case, what's so special about quantum mechanics.
Right.
So, yeah. So yeah, this is a big area of study in quantum computing, but I was interested in like whether let's say entanglement is the thing you can say is special about a quantum computer. And if so, then maybe entanglement is like super fundamental in quantum theory as well.
Right. That's very interesting. Yeah. Very different approach than experimentalists would take, for sure. And I definitely think that's highly useful. I've been seeing a bunch of times where people will keep saying, oh, we've got this quantum algorithm here, and then it just gets remade in a classical version, and it's like, okay, well, I guess not.
Yeah.
Exactly. So, it's because like most quantum, condensed matter guys like us, we would be more interested. At least for me, I'm interested in like putting things in superposition. I've seen research papers out there where some people have put paper clips in superposition, which is really cool stuff. Really cool.
That's really cool.
Yeah, really cool stuff.
Yeah, some macro objects. I don't even know how the hell that's possible.
Yeah, leaves my
head. Got an Avogadro's number of particles.
Yeah, exactly.
You either have to.
I don't believe it, honestly.
You don't believe it? Maybe
I
don't know. It was published a couple of years ago. Maybe it was redacted. Who knows?
Hopefully.
But yeah, that one. More that's an engineering feat, but nonetheless. We grapple with concepts of like decoherence and stuff, and I think I'm sort of, that's my kind of interpretation of how I interpret quantum mechanics in terms of measurement. Like we sort of drive the system into decoherence, and that's kind of the and we have to probe these foundations if we want to build really good quantum computers, right?
Right.
But
that's really cool. So basically you think that measurements are just decoherence?
Yeah, I've heard the arguments, and I think I kind of I think I'm more leaning towards that camp, but
I feel like Mithuna's got a
she's got a wrench to throw in there.
You got a rebuttal for one?
This is more about what I read a long time ago, so maybe there's new
No,
information.
I'm just really happy to hear you say that. That's what I think. Like, that's what the many worlds interpretation essentially is. And for some reason, this is very controversial, and I don't think it should be.
No, I don't think it should be either. It's kind of silly, but yeah, it's it seems to be the most realistic interpretation in my opinion.
Right. Yeah.
But
yeah.
Yeah.
No, you're right. So like what you were saying about those foundations issues, like becoming sort of like practically important issues when you build things. That's very true, because with like quantum computers, you need to be making superpositions with like very large numbers of particles.
Exactly.
And if you take this like traditional quantum mechanics view that there is like a divide between the classical and quantum world, and it just happens at some like size range, then you can't build a quantum computer. Like there's going to be some number of qubits where suddenly it's like, oh no, classical mechanics applies now. Everything is like not in superposition, which is obviously not true. So
right. Exactly. And that's something that I remember reading in literature papers and books as well, where they were saying, well, the quantum regime is anything below this, these many, whatever, now above this sort of size or whatever, no, quantum mechanics no longer applies, but those boundaries are constantly being like tested. So
yeah, exactly.
Yeah.
And I think that the truth is there is no boundary, right? This is, it's a problem, like it's a huge engineering problem to figure out how you stop this from decohering. But as long as you can make superpositions of anything.
Yeah. Yeah. And that's...
Yeah, it's really interesting.
I mean, how far out do you think... So you've studied this problem extensively since this is kind of your whole PhD thesis. Do you think... There's a lot of people that think, like... I talked to my advisor. He's like, this is all he sort of thinks this is all hogwash kind of thing. Like, this
nice, yeah.
This is like, so many years down the line. They'll figure it out when I'm dead. So... but do you think...
Wait, how old is your supervisor?
He's relatively young, I guess. He's like in his 50s.
Oh, okay.
Okay. I don't know. He's a very grim
He's
guy.
got some time. I don't know. Unless he's wishing for an early death.
I hope not. I hope not. He's a great guy, but like, but nonetheless, do you have in your mind? How far out do you think we are in terms of tackling this problem? Like making, I mean, I know it's an engineering problem, but I guess figuring this all out to having it be kind of common.
Yeah, that's a great question. And I'm not. What? Sorry.
I didn't catch Juan's question, but you go ahead.
Okay. No, so the question I feel like is like when will we have quantum computers?
Yeah.
Is that right?
Yeah.
Okay, cool. So yeah, like I'm not an experimental person, and I don't want to pretend that I am, because like there's been a huge amount of very good work in that field, and I don't want to like take any credit for it, because I clearly have done nothing. But what they tell me, and like what they tell like our field in meetings, is that it's like 5 years away for something that's like useful for at least even one application, or like maybe 10 years, and then maybe like 20 years, something like that, for a more full-scale thing. I wouldn't take those estimates too seriously, because obviously they're from people who have a huge vested interest in it actually happening.
Yeah. And also based on current knowledge and projections of whatever,
Exactly. So, I mean, it could go both ways. Like, obviously there's going to be unforeseen hiccups, but then also there's going to be great advances in the technology, so it's hard to say which way it will go.
Now, do you have a favorite quantum computer, like as in we have superconducting qubits, we've got topological insulators, we've got you pick whatever, we've got a bunch. Do you have a personal favorite? Even though this may be outside your realm, but
Yeah, no, I feel like you're trying to ask this question so I can't get hired by various companies.
I love them all equally. They're all my babies.
Exactly. They're all equally good except the one that will pay me. That one is the best. Okay, this is very much outside of my field. Like, to me, when I'm writing the maths, a qubit is a qubit. It doesn't matter what it's made of, which is obviously not true in the real world. But one interpretation that seems, one architecture that seems like potentially promising from a theory point of view.
Oh, restart the camera.
You're good.
Okay, so one architecture that seems promising from the theory point of view is the superconducting qubits that Microsoft's been working on, I believe. Because what's great about them is they have some error correction built into them. The thing that's not great about them is that they don't exist.
So what do you mean by they don't exist?
As in, they've never been able to get qubits happening.
Oh. I see. Because the state has decohered too fast.
So this goes into like some physics stuff that I don't know about. But it kind of requires some exotic states to exist, which people still debate.
I see.
Oof, I don't know if they should have built a whole quantum computer.
So it's what the industry
calls a little bit of a dice roll.
It's what the industry calls a white paper, where it's kind of just like, well, this is all true in principle, and maybe we can find the right thing to have it work.
Yeah.
But you would usually think industry would stay away from stuff like that.
Right. It's a huge gamble, and Microsoft.
Yeah.
Maybe they just have enough money and they're just fuck it.
Oh, they do.
Whatever.
Yeah.
Hats off to you, gentlemen and women over
Bill
at Microsoft.
Gates. Actually, he's not really involved too much though anymore.
I don't think he is. But I think it's great because if they do find these states and that part gets worked out, then suddenly they can take advantage of like this huge amount of theory that has been built up around it, and they'd be like well ahead of everyone else. So it's a really risky gamble, but it could pay off.
So why does this error correction for those listeners out there? Maybe you can explain a little bit of that. Like how does error correction play into a quantum computer?
Yeah, so error correction in like a classical computer is just like, well, when you have these bits with all the information on it, they could get corrupted, and if they get corrupted, like you can't recover that information. So one way to error correct is when you encode the information, why don't you encode some redundancy into it? So a very bad error correction code that you could use is like, oh, let's just copy all the information 3 times. So if like one of those gets corrupted in some way, I can just look at the other copies. This is not how you would do it, but like you could imagine something like that in theory. But for quantum computers, error correction is a very difficult problem because you can't just copy things. Like there's this no cloning theorem in quantum mechanics, and so you can get around it. There's some really clever ways to error correct, but the issue with that is it tends to inflate the number of qubits that you need hugely. Like, I don't want to say any numbers right now because I'll definitely misquote it, but it's insane. Yeah. Like, to run, Shor's algorithm that should, use, like, let's say 100 qubits or so, suddenly you'll need, like, millions of qubits.
Oh, wow. Wow. So orders of magnitude.
Yeah.
Oh, wow.
It is. It really is orders of magnitude. And so that's the real problem. Like, so there's 2 ways that this could get fixed. Maybe eventually qubits will become so much easier to manufacture and so much more reliable, in which case, like, that would bring down those numbers a lot. Because if you can make every qubit, like, more reliable, then you need less of them. So that's, like, on the engineering front. But on the theory front, there's been this huge effort to come up with better error correction codes, which it just seems really hard. But if that could be done, that would be a huge breakthrough. But if neither of those really get to that level, like get to the level we need them to, then what you'd like to do is like get around error correction as much as you can. So these like superconducting qubits that Microsoft's working on sort of have this like natural error correction in them that would mean they wouldn't like have such a bottleneck.
Mm-hmm. Interesting. Very interesting. Yeah. So, quantum computing's got a few ways to go, it sounds like.
Oh, yeah.
It's a long journey. I don't really, well, maybe not long, I don't know. It's one of those things where we're not really sure how long it's going to be. But best of luck to all the people out there, and of course you as well.
Yeah. Well, real quick, I want to stop. I'm going to pump the brakes because I still have more. I have one more question.
You're sucking up all the time.
Yeah,
we got to go into.
I'm curious about all this. This is also fascinating to me. I don't know if you. I mean, I don't know if you necessarily have an answer for this, but I've always wondered what's the differentiate. Like, how can you tell the difference between a classical algorithm and a quantum algorithm? Is that something that's like immediately obvious, or when you're doing this kind of stuff, or is it?
Okay. So is this related to these algorithms that sort of recently got dequantized? Like, people figured out that you could do them classically.
I guess, yeah. I mean, I'm just. This is more of like just a question I just thought about. Like, I'm just kind of curious if you know, if you.
Yeah.
Yeah.
So when you write a quantum algorithm, what you're doing is you're starting off with some qubits in some state. Let's say that they're all in the 0 state. Mm-hmm. So like, how bits can be 0 or 1.
Yeah.
So you can imagine all your qubits in the 0 state. Then like your algorithm basically is like, what quantum operations are you going to apply to these as they like evolve through the computation? So there are some evolutions that are only allowed by quantum mechanics, right? Like you could imagine, like let's say I just have one bit, or one qubit, and then I want to apply something to it that puts it into a superposition of 0 and 1. Like that like evolution is just not allowed in classical mechanics. So that's not a classical algorithm, because like that's just, you can't do that on a classical computer, right?
Right.
And so like, a quantum algorithm is really anything that like uses quantum mechanics for the evolution. But then there's like this more subtle point, which is like, sure, let's say that you could make your qubits go into superposition during the computation. Does that mean that you've done anything that's like better than what you could have done classically? Like, sure, you can't do that exact thing on a classical computer, but maybe you could do something else that will get you the answer in roughly the same time. And so that's like the big debate. Like, we don't know yet whether quantum computers, like the algorithms that you write for quantum computers, that you can't write equivalent classical algorithms that would be just as good. So as an example, like the quantum algorithm everyone talks about is the factoring algorithm. So if you're given a big number, find its prime factors. And like lots and lots of people for a long time have tried to find an algorithm that solves this problem quickly on a classical computer. The reason, of course, is because encryption depends on this. And so lots of people have tried to hack encryption and so far have failed, which makes us think that maybe there isn't a way to do this quickly on a classical computer, but there is an algorithm that allows you to do it quickly on a quantum computer. And so this gives us some evidence that there are quantum algorithms that are very efficient, that you can't like kind of mimic on a classical computer. But we don't know for sure.
I just thought of an interesting, weird question.
Yeah.
I wonder if there are any quantum algorithms that are worse than classical algorithms.
Yeah. Oh, yes, absolutely. Right. Like, you can write stupid algorithms however you want. But you can always guarantee that there is a quantum algorithm that is as good as the classical algorithm. And that is, just run your classical algorithm on your quantum computer. Your quantum computer can run any classical algorithm, but the other way around is not true.
Interesting. So the quantum computer can always run every classical computer algorithm.
Yeah.
Interesting. But then so my question with the worse algorithm, would that quantum can you have a worse algorithm that's solely quantum that a classical computer cannot run?
Yeah, so imagine that you just had, so imagine like you want to solve some problem, like this is what you want your algorithm to do, and how you're going to do it is you're going to like do some, sensible classical algorithm, but first on your quantum computer, you're just going to like mess around. You're going to take your state, you're going to put it into a crazy superposition, then you're going to take it out of that superposition, just do this a few times, and then you're going to do the sensible thing.
I see. So I guess more what I was thinking was maybe less like arbitrary. So like the quantum algorithm, those are like arbitrary steps to just make the time. It's like kind of artificially boosting the time it takes.
Totally.
I wonder if there's any quantum algorithms that are just, you trim all the fat of the algorithm. Is it worse than in a classical algorithm? Is there any such algorithm that exists there? that you know of?
Yeah, so I mean, I don't think this is a particularly quantum thing. Like, I think, let's say that you know a good, like, let's say you have a problem that you want to solve. You can write a good classical algorithm and you can write a bad classical algorithm. In the same way, you can write a good quantum algorithm and you can write a bad quantum algorithm.
I see.
So you're just solving the problem, not in the best way.
Okay, that still sounds like the fat needs to be trimmed, though. But
right,
who
but
knows?
No, like, it can be... So, like, you know, as an example from the classical world, prime testing is this question where you have a big number and you just want to know whether it's a prime number or not. And for a long time, people didn't know how you could solve this problem efficiently. So the algorithm that they might have used is just like check whether it has factors, which is obviously very inefficient because you just have to like check heaps and heaps of factors to see if they divide it, which is obviously dumb. But I can't remember exactly when, but someone came up with a very elegant algorithm that checks very efficiently whether it can be done, like whether it's a prime number or not. But those two algorithms, like the checking one and the nice one, they're very different, right? Like they get it like a different. I don't know. All I'm trying to say is that the other one, it's not that you just have to trim the fat and then you'll end up with the better algorithm.
There's some kind of uniqueness to the two. Gotcha.
Yeah.
Gotcha.
Yeah.
Okay, I'm convinced.
Okay, good.
All right, cool. So we're sitting around an hour here. So let's start wrapping it up a little bit because I want to make sure that we have the video. But I guess to start closing it out here, Mithuna, so I wanted to end a little bit on your YouTube stuff. So we've noticed that you had a very particular style to your videos. Of course, the name would suggest Through the Looking Glass or The Looking Glass, but it comes from the I think it's author of Alice in Wonderland, I want to say. What inspired you to go the Alice in Wonderland route?
Right, so people may not know this, but Lewis Carroll, the author of Alice in Wonderland, was a mathematician. And so he wrote two books for children. The first was Alice in Wonderland. The second was Through the Looking Glass and What Alice Found There. The second book is one of my favorite books of all time. And part of the reason for it is like, okay, partly it's just like an ode to childhood and like the curiosity of children, which I think is very beautiful. Mm-hmm. And I think that more people need to, be more curious. And I think that's like something that I wanted the channel to be about. But then secondly, there's a lot of very interesting mathematical illusions in the book. And so I wanted to like sort of play on that and like use the characters to be characters in this like mathematical story in the way that they are in Through the Looking Glass.
Very cool. I like it. And you draw all the pictures yourself too, right?
Oh yeah, I'm like a terrible artist. So I do draw them all myself.
I was like, are you like, do you do art on the side? Or
you're being very humble right now.
Because sometimes you'll do some of the quick ones on the drawing board, but you also draw do you draw like the Alice figure and everything too?
Yeah.
That's really good.
Thank you. Anyone that looks halfway decent took me hours. So like I'm really not good, and I've always been like thinking like, oh, I should practice. I should like get good at this one day. But it's always been like at the bottom of my list, and so this is how I do it for now.
I see. So you never did like drawing as a kid or anything?
Oh no, I loved art as a kid. Yeah, I at some point was like, oh, I'll be an artist. And then I was clearly, I went into physics and everything and stopped drawing. So now,
yeah. Sounds familiar with me. Like when I was a kid, I used to draw all the time.
Same.
Oh, really? What you draw?
In like too long. These skills dwindle over time.
Yeah, I mean, absolutely. But I think it's really sad. Like I think that people doing physics or maths or whatever it is should put some effort into having more breadth, and those skills are actually really valuable.
No, I do find. I don't know if you have this this sort of experience, but I find that most Well, not most, but there's a good chunk of physicists out there that have some creative background.
It's usually the ones that go through the same tail as as Mithuna and us.
Yeah, okay.
You know,
right.
go the really long trajectory, it seems, that are more the creative types, I've noticed.
Right.
Yeah, but they usually... Yeah. I don't know if you've experienced that as well, if you've seen that, yeah.
Mm-hmm.
Yeah.
Yeah, definitely. I think it's funny how many physicists can play an instrument. Like, I can't. I don't know if you guys can.
Yeah, we both do.
We both do, yeah.
Yeah, there you go.
I've actually been writing music this whole week.
Yeah.
Right, exactly. Right? And I think that, like, it's a lot higher than the general population.
Yeah, because I find a good chunk of people, even new students that I meet, and I'm just like, hey, you play an instrument too? And they're like, yeah, blah, blah, blah. And
yeah, exactly.
What instrument do you do?
No, I don't.
Oh,
so I'm one of the...
you're the
uncreative
outlier.
ones.
No, I'm just kidding.
Well, she does. She does the art, and you also said you know Japanese too, so you're into foreign language.
Right. Yeah, I guess so.
Yeah, I'm just trying to remember all your eclectic abilities there.
Wait, nani? How do you say that?
Do you also speak Japanese?
No, I'm kidding.
We just know the meme.
Yeah, we know the just from watching anime. A couple times.
I know.
I know Hadouken.
Shut up.
Yeah. Oh, very good. That's a useful one. Actually, I stopped myself watching anime at some point because I realized I was learning all these bad words that really aren't useful.
Too colloquial, too vulgar, too conversational.
Just to throw it in there real quick, do you have a favorite anime?
I have so many.
No, you got to say one or just at least one or two.
Give us three. Give us three that no tier. Just say three that have left a good impression on you.
Okay. Well, so I used to read more like manga than I used to watch anime, but
true fan.
But
she's high level.
Oh no. So like these are really old ones, but I used to really love Hana Yori Dango, which is I think got made into like into a drama and stuff.
Okay.
An anime probably.
Okay.
And Fruits Basket. I don't know if you guys watched that.
No.
Never heard of it. There's so many anime.
Yeah.
And then obviously I'm a huge like Clamp fan, so I love Kaikata Sakura and
that one's
I'm blanking. Whatever.
These sound legit.
Like Tsubasa and all of those Clamp.
Yeah, Card Captors. Even I watched that back in the day. Like I haven't heard that in a long time.
Wow.
What's that one little character's name who sounds like I forget his name. He's like a little mini lion.
Yeah, Kiraberis.
Yes. I used to love him. He was a great character. That show was great.
That show was great.
Yeah, but that's cool.
Good stuff.
What about you guys? Are you guys big? This is
big anime fans?
Is not. Yeah.
Yeah. I'm a guy who likes only very, very few anime because I don't really like anime.
Right.
But the couple that I do like, I really, really like. So
which ones?
My top two animes are Berserk and Death Note. I just literally rewatch those every time.
Those are very Americanized
I don't think I've heard
takes.
of
them. So Berserk is a really, really dark anime.
Don't watch it, folks. Please.
You may not. I don't know. It depends on how much you can stomach.
Don't even Google it. I'm being 100% serious.
The story is so good, though, and the characters are so, like, real to me. They just seem like such... Yeah. It's not like tropey. There's no... Everybody has, like, three-dimensional qualities to the characters.
Right. Yeah.
And then, of course, Death Note is just really cool because it's like basically a giant chess game in anime form.
Yeah. Right.
Yeah. So I love those animes. I just rewatch those every year.
Yeah. So like Death Note. Sorry. Go on, Juan.
No, I don't know if you were going to make a comment on Death Note. I think.
Oh no, I was just going to say that like Death Note is one of those things that like the fans seem really into it, and I've never been able to get into it because it's just so long.
Yeah.
Seems like a huge investment.
Just watch up to episode like 22 or 23. After that, I stopped. You'll know.
Okay, I'll just watch 20 episodes. No worries.
No, well, for me,
we're just gonna watch one a week. You know.
Yeah. Well,
right.
For me, I'm very casual. I'm a very casual watcher. Most hardcore anime fans will probably not like my answers, but I've watched.
Don't say Dragon Ball Z or you're done.
That's the one I grew up with, so that always has a special place in my heart. But,
exactly.
But the only up to the Cell Saga, okay, and then maybe Super. Super was pretty good.
Yeah.
But
I agree.
This new one was pretty good. But
you agree? Oh my god.
But the other ones are Steins Gate. I really like Steins Gate. It's about time travel, and there's a eclectic physics guy who's discovered how to time travel using a microwave. It's also really silly, but it's also it takes a turn. So it's kind of interesting. Yeah, there are a couple other funny ones.
One Punch Man is great. That was actually pretty funny. Have you seen One Punch Man?
I've seen some of it.
It's really silly.
Yeah,
it's funny though.
I like kind of funny animes. There's I had to run for a while watching Soul Eater. That was fun. And then I also watched that one's not my favorite, so I just honorable mention for that one. Okay. But I swear I'm going to wrap this up. I have two more.
Hurry up.
Two more. I want to make a shout out to The Devil was a Part-Timer. I think if that one's on Netflix, I think it was.
Okay, I haven't seen that.
That was really funny.
There's too many anime.
That was really funny.
Too many.
Long story short.
Yeah.
Satan comes from another universe, and he comes to the regular human world. He doesn't have powers, but he's still internally Satan, and he believes a lot of satanic things, and it's really silly. He has to get a job at McDonald's, and it's really funny. Go check it out if you have it.
Sounds great.
And then last but not least, Attack on Titan I think is really great. And I haven't seen it recently, but
overhyped anyway.
Yeah.
Yeah.
All right.
I got a couple more. I just realized I have a lot in the bucket.
You do. We don't have time.
What?
So anyway, thank you for coming on, and thank you for this really great discussion.
Yes. Put some applause in the post. Mithuna, you've been great.
Yeah, this was awesome.
We really had a good time with you here.
Yeah,
I feel like we could have gone for probably like another hour or two.
I know. It's been really fun.
Yeah.
Thanks a lot for having me.
Yes.
It was our pleasure.
Just to plug your stuff, guys, make sure you check out Mithuna's channel. It's the Looking Glass Universe. She's also on Twitter.
Go ahead.
Mithuna, do you have any other plugs that you want to throw in there?
No.
Plug in your Twitter.
I try really hard to basically only have one social media. So I have a Twitter technically.
Okay.
But don't follow me.
She's a busy lady, so guys, just go to her YouTube, add some more subscribers. Actually, it's probably really you guys are coming to us.
No, we have a decent fraction. We have a strong core. You know,
that's true.
We have a strong core, and
so our several hundred listeners, guys, go to Mithuna's channel.
Yeah. All right, thanks
You'll
very
love
much.
her content, we promise.
Yes.
And thanks for coming on.
Yeah, thank you.
Mm-hmm. See you later.
Bye. Okay, I just stuff all these.